freezer. Today we're investigating how quickly light beer freezes and how long we can keep a typical beer bottle in the freezer before it bursts. Today we'll perform 3 experiments. First, we'll observe the freezing and volume expansion of beer in a graduated cylinder. Second, we'll observe multiple scenarios of the time it takes for our beer to begin the phase change process and calculate the mean value of that time. Lastly, we'll observe multiple scenarios of the time it takes for our beer to burst open in the freezer, and we'll calculate that mean time and the minimum time. Here is the data for our 3 trials. In each case, the starting temperature is a little different and the volume of the beer is a little different. What is noticeable here is that the freezing time increases with volume increases, even when the starting temperature is higher for the same volume. Did you notice in each trial that the temperature falls below 32 degrees Fahrenheit? Did you also notice that as the beer freezes, the temperature comes back to around 26 degrees Fahrenheit? This is a phenomenon known as supercooling. Supercooling is where liquids cool down to below the phase change temperature for some pressure, but as soon as a nucleation site is found, freezing of the liquid to a solid then occurs and the phase change is underway. There are videos on YouTube showing this phenomenon with various beer bottles, and there was an episode on Mythbusters that also showed this. I got curious if I could show this in a graduated cylinder, and how much vibration was necessary to induce the process. As it turns out, not all that much. We can get a rough estimate of the phase change temperature by considering a simple model of the chemical species composing the beer. We'll assume the beer is 4.6% ethanol, which is a common alcohol found in beers and spirits, and 95.4% water, or H2O, both by volume. We'll use some data compiled from the Engineering Toolbox website as a reference for freezing temperatures of water-ethanol mixtures at varying concentrations. Here is the data from the Engineering Toolbox. Here is a curve fit of the data between 0 to 50% concentration. The light blue star indicates the calculating freezing temperature, about 29 degrees Fahrenheit, at a 4.6% ethanol concentration. This is pretty close to the approximately 26 degrees Fahrenheit temperature we observed freezing in Experiment 1. In Experiment 2, I wanted to determine how quickly a full bottle of beer would reach a temperature of 26 degrees. The bottles are open in this case, and I use a little piece of cardboard to hold the thermometer's bulb in place at about the center of mass of the bottle. I performed 9 trials of this experiment, 4 in one freezer and 5 in a different freezer. It was discovered after the experiments that the first freezer occasionally malfunctioned, so I will gray out that data and will focus on the 5 experiments where the data can be trusted. Note that the freezing temperature is again approximately 26 degrees. Trial 1 through 3 was an open-top trial, where I would open the freezer and take a quick measurement with a digital thermometer. Trials 4 and 5 were closed-top, where the beer was left in the freezer and then opened at the 45-minute mark and the temperature taken. Note that the curves have inflections, where at first the curve is like a downward parabola and then starts to look like an upward parabola. This may be an observer effect, due to me opening the freezer every 5 minutes to take a temperature reading, and adds uncertainty to the experiment. In our third and final experiment, we try to find out how long a beer can sit in a freezer until it bursts. 10 trials were performed in total, 6 where the beer is standing up, and 4 where the beer is laying down. In 2 of these trials shown here, we can make out the temperature creeping up as high as 20 degrees Fahrenheit, which is how I figured out the freezer is malfunctioning. The freezer temperature is set to 0 degrees, and eventually it gets down there and it remains relatively close. In case anyone plans to repeat this experiment, a tip. Trying to time-lapse your phone in the freezer won't work. The very cold temperature makes the battery die well before the beer bursts. Instead, use a snake camera and time-lapse the actual screen. Experiment 3 data appears to show that the bursting time is about 7 hours when the beer is standing and nearly 9 hours if it is laying. However, recall that the temperature of my freezer was fluctuating much more than expected, which probably has some effect of lengthening the time to burst. In each case, the beer was approximately 38 degrees initially. I've written down initial conclusions because I'm not fully convinced of these results. The fluctuating freezer was surprising, and may be faulty equipment, which is why I've decreased the time to freeze down by 20%. Additionally, I would have expected the temperature to follow an exponential decay like in our coffee experiment, not have a hump as shown in the Experiment 2 data. I think I owe it to science to reperform these experiments once my equipment has been checked and calibrated. So keep an eye out for freezing beer 2. But until then, thanks for watching.